Hello everyone, Aaron here and welcome back to Leetcode. Today we are doing the perfect squares problem. Given an integer n, return the least number of perfect square numbers that sum to n. A perfect square is an integer that has the square of an integer. That is the square of an integer. In other words, it is the product of some integer with itself. For example, 1, 4, 9, and 16 are perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16, while 3 and 11 are not. These also happen to be primes, so obviously they're not a square of anything, but numbers like 8 are also not perfect squares because they're made of a 2 and a 4, for example. There's nothing you can times with itself to get to an 8. So if the input is 12, we can do this with 3 numbers, 4, 4, 4. If we did it with a 9, we would have 9, 1, 1, 1. And that would be 4 digits. Aha, okay, that's interesting. And if we do it with 13, we could do it with 2, that would be a 9 and a 4. So what this example is showing us is that we can't be greedy. So a greedy algorithm is one that just takes the best looking option and goes from there. So if we're trying to make 12 using 1, 4, 9, and we don't need to use 16, using 1, 4, and 9, a greedy algorithm would say we should start with the 9 because that will get us most of the way. That won't work. There is no use taking this 9 because it'll force us to then take too many 1s. We're better off skipping the 9 and going to the 4s. So that means we can't use a greedy algorithm. We can't just do what looks best at every step. We need to be more clever. And that probably means dynamic programming. So, let's start with the easy bit. Let's work out what are the squares that I'm allowed to use. So, squares is going to be an empty list. In fact, let's be fancy. Let's use Python's features. N times n. I times I. I times I for I in range 1 square root of n plus 1. So this says I'm going to start at 1 and count up to the square root of n plus 1, but that's because this count is exclusive. So let's say the number I was given was 16. The square root of 3, 4. Now if I just put the square root of n here, maths for this, don't I? Or is square root a built-in? Square root might be a built-in. Maybe I don't need to do that. We'll come back to it. So I need to do the plus 1 just because range is only half open. I don't need to include 0, so I start at 1, because 0 squared is always 0 and it's never going to contribute anything to a sum. So this is my squares that are relevant to this problem. Why don't I need to search all the way up to n? Because I'm doing a square, if I was doing square root of n plus 2, so there's 16 square root 4 plus 2, that's 6, that means I'm counting up to 5. There's no point checking 5 because that's 25. I'm not going to use 25 in a sum to make 16. So that's all. If it's not a perfect square, the number we're searching for, say it was 15, the square root of 15 is going to be 4 point something. So that means we're only going to count up to 4, but that's okay because that will overshoot anyway. Right. So now we've got this. I think what we are doing is There's a fairly famous problem in algorithms called making change, or change making. And the idea is that imagine you have a set of coins. So if you have a 1p coin, a 2p coin, a 5p coin, a 10p coin, those kind of coins, and you're trying to make change for 86p or something like that. What's the way you do that? Now, the way that coins are designed in the real world is that they do allow for a greedy property. If you're making change for 86p, you can take a 50p coin first, because the remaining coins aren't going to make that a bad choice at any step. Here, this is effectively our set of coins. These can allow you to take a bad step. So what we need to do instead is a recursive problem. What I can do is I can say, if I'm trying to make change for 12, I can try taking 9, and then I need to work out how to make change for 3, because 12 minus 9 is 3. That's then what I need to make change for. So then I ask, well, how do I make change for 3? Well, that's going to be, I can take 1 off, then how do I make change for 2? And then I can take 1 off, how do I make change for 1? And then I can unwind that stack and go, well, I had to use one coin to make 1, then I used 1 extra coin to make 2, and then I used 1 extra coin to make 3, and then I used 1 extra coin to make 12. So that's 4 coins altogether. So that gives us one option. And then we can try again. Well, what if I didn't take 9? What if I took 4 instead? Well, that would then have me ask, well, how do I make 8? And then, okay, what can I do with 8? Well, I could use another 4 coin. Then how do I make 4? Well, 4 is one of the coins, so I know I can make that in one step. So I use 1 coin to make 4, and then use 1 more coin to make 8, then use 1 more coin to make 12 for 3 coins altogether. So that means we're going to need some function. So the idea is, what values can I use? So what I want to do is, the idea is I want to, how can I do this? I'm just trying to think what's the best way to do this. If I want to find the max coin index, the max coin index is the max enumerate values, key is lambda v1 v0. Let's make that a negative v0 so that earlier indices come earlier. There should never be a tie, so this one shouldn't matter. So what this does is it finds me the maximum index value pair sorting by the value. That gives me the maximum. No, if we assume these are sorted. No, that's not right. That's not right at all. Let's do this slightly differently. Max coin index is len values -1. That's not how you spell while at all. What went wrong there? While values max coin index is greater than the total, max coin index minus equals 1. So there's no, so that just whizzes down to find the largest coin we should start with. Then what we want to do is say the options are, well, no, what do I want to do here? Min number of coins is equal to, let's start with infinity, while max coin index is greater or than or equal to 0. What I want to do is say the target is the total minus the coin at the max coin index. Number of coins is going to be 1 plus the number of coins we use to make the sum of the target using the values. Actually, what I could do is I could pass down max coin index, couldn't I? The last coin used. That way I don't need to start at the end every time. I know roughly where I'm looking. If number of coins is less than min number of coins, in fact, we can make this even quicker. Min number of coins is the minimum of the number of coins and the minimum number of apparently I believe in long variable names today. Return the minimum number of coins. Right. So this does what we said before. We said, how can I make 12 using a 9 coin? Well, I can take off that 9 coin, work out how to make 3, and add 1 to the result, and keep track of that. And that was 4 coins. Or I can do this with a 4, and then work out how to make 8, and then add 1 to that. And store that, if that's our new minimum number of coins, which is 3. And then I try again with a 1, and that's how do I make 11, and so on and so forth, and then we'll return 3, which is the minimum number of coins. We can probably do a check here. If values of max coin index is equal to the total, so if this coin is in our, if the total we're trying to make is the coin, then we're done. We know the way to make that is with 1 coin. There is no better option. So down here, what we want to do is we want to return the make sum for n with the squares len squares minus 1. So let's run this, see if it actually works. Float cannot be interpreted as an integer, so I need to do an int around that. That's fine. It's taking a while. I knew it would take a while. Time limit exceeded, yeah. So I knew this was going to happen. I was hoping it would work, and then I could do a whole explanation about how it's too slow. But it's just straight up too slow. And the reason it's too slow, well, let's print it out. And then let's start with something smaller. Let's go with 5. Hopefully that'll be fast enough to actually pass the test so we can see output. No, it's not going to be fast enough just so we can even see the output. So I'm going to have to just explain. The reason it's too slow is because it's doing a lot of the same work again and again and again. Making these change options, we're going to end up being asked to make change for 2 or 7 or 8 or whatever, these smaller coins really often. I think that may just be stuck now. It's not even timing out. So what we actually want to do is we want to wrap this. We want to say change maker factory. Oh, it just bugged out completely. And the idea is we want to go up to n. And so what we want to do is we actually want to keep track of all of this. So I want to have a non-local cache. If cache total is not none, return cache total. Return make sum. So the idea here is we need a cache. And the cache is going to be a list of nones. And it's going to be up to n. And in fact, what we could do here is take the values as well. So then we don't actually need to pass through values in our make sum. So frog in my throat. So we've got this cache now, and it's got nothing in it, but we do check it just in case. But down here, what we want to do is I want to set the cache of the total to be equal to the minimum number of coins. I don't actually know if I need to say this, but I will anyway. So we've got this cache now where we're saving the minimum number of coins for every total. So if I've done the computation before, for example, how do I make 8 change, I can now just look it up. I will immediately know how to make change for 8. And this works at all levels of the recursion as well. So what I can do here is I can now say make sum local is the change maker factory initialized with n. Actually, I need to do this with n plus 1 because there's a 0. I need an index for n with the squares. So let me just good gracious, I want to copy that. I want to reload the page because it's broken. I think that works. So let's just see what's going on. Hello. Time limit exceeded. Ooh, that's more surprising. I did expect to pass it this time with the cache involved. That's very strange. Time limit exceeded. Okay. Print the total with the cache. And let's do it with 4. Cache is up. Well, let's try it without those non-local declarations. I don't know if they're necessary anyway. Oh, that worked. Oh, what I can do here is for v in values, cache v is equal to 1. I know that by default. So I don't actually need that check anymore. So let's run it, see what our cache looks like. Ooh. Oh, yeah, because 1 is set to 1. So let's try it with a 5. Oh, my goodness. I know what I'm doing wrong. It's been slow for a completely different reason. I wasn't decrementing max coin index in my loop. I'm an idiot. I do apologize for all of you who have been screaming at the screen that I am dumb as a sack of hammers. That was not at all my intention. I do apologize. So, now let's run it with 12. Okay, excellent. So we're seeing we're doing 12, and then we take off the 9 to try it with 3, 2, 1. So that counts down like that. And we see there we've actually filled in a whole lot of the cache. It bubbles back up and says, well, I can make a 1 with 1 coin, a 2 with 2 coins, a 3 with 3 coins. We've got the 4 and the 9 with 4 and the 9 with 1 coin each. And then it tries again with the 8. And obviously we don't know how to make an 8. We do know how to make a 4. Interestingly, it didn't write in that we know how to make the 8. Oh, because we don't know if that's the minimum number of ways to do that yet. The 7, 6, 5, 4, we try down, so we can burrow those all the way back up. And then when we go to try it with the 11, 10, 9, we see it's remembered a whole lot of different things. So let's get rid of that printing. We don't need that. Excellent. Use all the test cases. The largest value we can have is 1,000. So let's run it with 1,000. Which you can make with a surprisingly small number of coins. Let's try it with 999 and see if that gives us a more perverse case. A little bit. You can still make it surprisingly quickly. Excellent. I think this is working now. I'm curious as to what would happen if we didn't do this. Would it be too slow? It's noticeably slower, which is a good thing. That means our cache is doing something. Yeah, time limit exceeded. So you do need to do the memoization. So this is a trick called memoization. Python actually has this in its standard library called an LRU cache, a least recently used cache. And the idea is that this, we know how big it can be, but in general, if you're doing memoization, you don't know how big your cache can be. You could have many intermediate values that you need to look up. So it has a least recently used cache, which means the least recently used value will be forgotten if it ends up using too much memory. That's just to make sure your program isn't horribly wasteful. Right, let's submit it. I waffled on for long enough. Ooh, that's unexpected. A wrong answer. 7168. I said the best way to do it was 5, and it thinks I should be able to do it with 4. So does that suggest this bound is wrong? Let's print the last 3 squares and also the square root of it. How could this have gone wrong? That's what I don't quite understand. How could this have gone wrong? I think it uses 5 coins. This is going to print too much, I suspect. Yeah. I don't want to have to update the code to trace what it thinks is the right way to do it. What is the case where it's gone wrong? I think I need an extra coin for some reason. What on earth could the extra coin be? And what's special about 7168? Show me all the squares. Don't know. Looks like I'm going to need to instrument this in some way. Now this is very strange. What have I done wrong? So I've got the cache. Walk down and find the largest coin that I can possibly even try. The minimum number of coins is initially infinity. Max coin index, while the max coin index is greater than or equal to 0. While there's coins to try. Target is total minus the values of the max coin index. The thing we're trying to make minus the coin we're trying to use. How do you make that new value? You're allowed to use repeats. Then just make sure we're always using the minimum. And the max coin index gets decremented. We save the minimum number of coins. And then return it. That seems good. This should make sure we get a new one for every run. Wow, is this problem going to beat me? What the heck? Okay, let's instrument this. Number of coins plus equals 1. Path is equal to path plus values max coin index. If number of coins is less than min number of coins, min number of coins is equal to number of coins, min path is equal to path. So we've also got a min path. So this is going to be 1 this is min path. This gets a min path associated with it, and this gets a v path associated with it. Count path, return count, print path. So how do we think we do it? Oops, min path is equal to none. We think we do it with a 4, 4, 4, 100, 7,056. That's 7156, 760, 7160, 7168. Yeah, that works. So where did we get it wrong? I think I want to just see what the cache is. So the first few are all doing exactly what we expect. From pprint, print, import pprint. Show this to me nicely. Right, where... We're using a lot of ones. There, for example. Okay, so hang on. 11. No, I need to do a... Actually... No, hang on. Revert that back to 7168 for a second. What was I seeing there with an 11? Oh, it was, yeah, pprint enumerate cache. Oh. The list of the enumeration of the cache. So I was seeing a lot of repeated ones there. So 53, for example. 53 should be a 49 and a 4. So why is 53 wrong? Nope, it's correct. 53 there was computed to be a 2, a 49, 4, and a 49. Oh, is this wrong? Oops, no, not that bit. No, that bit was fine. Oh, I can't undo. I don't need this line anyway. This max coin index. I don't think I want that at all. I think I want to get rid of that. And the reason I think I want to get rid of that is because if I have to use a 1, I then want the option to be able to use a 4 again. I was making a greedy assumption that doesn't exist. So if we go back to our 7168, yeah. Oh, that's sneaky. So if we go back to, what was it, 53? Yeah. So for some reason there, I hadn't been able to use a 4. Now that doesn't make sense. Anyway, that saying that I had to use the coins before a certain position was limiting me too much. We needed the option to be able to go back and try larger coins again. And I guess that makes sense. If we want to do, well, imagine we didn't have the coin for 9. If we want to do 9, I'd take 1 coin off to do 8, and then I want to use 2 4s. Yeah, that makes sense. In fact, 10 probably would have been wrong as well. No, you can make that with a 9 and a 1. I don't know. It's actually surprisingly hard to come up with these kind of test cases. But they exist, which is why they're in the test cases. Time limit exceeded. Ah! This is a surprisingly hard medium. So now I'm not short. Oh, is it? That worked fine. Let's stop passing around all of this extra crap that we don't need. That's possibly making things slow. Shouldn't be, but just in case it is. That's a 1 again. That's no cache. There's no path. In fact, I can turn that just back into a return. Need to beat 145. We went slower. The problem is, I think this is going to be a flaky test. Let's just submit and see if we've improved things. Oops, I don't need that anymore either. Maybe I haven't improved things. Random time limit exceeded with a different test case. I'm floating right on the edge, I think, of a time bound. Okay, I'm going to reinstate max coin index. But I'm going to do something a bit different. So coin index is max coin index. This is going to be max coin index. But this is just going to be coin index. This is just going to be coin index. And the thinking here is all this does is bound it to a sensible range of coins quickly. So I don't have to start scanning all the way from the end of the coins every time. Huh? Index out of range. Values max coin index. But the max coin index is the length of squares minus 1, and values is squares. So there's absolutely no chance of that being true. Have I got a... Oh, that needs to change as well. There we go. Was that faster? Who knows? Let's find out. Oh, I should have tested it with our 7168. Still too slow. That's fine. Let's just go back to checking that one. Okay, so it's still working on the previously dodgy case. 8441 is fast enough here, but not there. I kind of want to go back to passing through coin index. But that breaks that. How can we make this quicker? I guess what I could do is also pass down what it's trying to beat. No, that doesn't work either. Because if I pass down what it's trying to beat, that doesn't speed it up, because it's still trying to minimize. This here is not that slow. This recursive call can be slow, but we've memoized it so that it shouldn't be slow. show me the cache. Maybe it's not getting updated early enough. I had a little inkling about that earlier. Oh my goodness, this is going to be useless. 20. Print total as well. Trying to do 20, I'm trying to do 4. That's all right. Then I'm trying to do 11. So in the next round, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why was it 11? Oh, because I'm still trying to compute the 11, aren't I? So I don't finish computing the 11 until I'm back to here, at which point, yes, I do I do fill in the 11. But that's all right, because I'm not going to use the 11 yet. Here I compute the 3. Yeah, that's getting filled in at the right times. So that's not the problem. The cache is not bad in that sense. The other way we can try this is, rather than doing recursive calls, is to just iterate through this list, basically build the cache explicitly. So for I in range 1 n plus 1, then what I want to do is if cache I continue is not none. And then it's going to be min number of coins is float inf how do I want to do this? Max coin index is len values minus 1. While max coin index, excuse me, is greater than or equal to 0. If values max coin index is greater than I, continue. Min number of coins is equal to min number of coins, or 1 plus the cache of I minus values max coin index. So this is a rather different formulation of the same idea. The idea is we know the cache is already filled now. We're not going to do the function call and see if it's filled. We're going to assume it is filled because this value comes before I, and we've already looked at all the values before I. If the value of the coin is equal to I, then we should have already caught it up there. So we will continue working our way down. X coin index minus equals 1. minus equals 1, and then it's going to be cache of I is equal to the min number of coins, return cache. So now we don't want to do any of this. Is it that? No. Is it that? No. I've forgotten the hotkey for commenting on Leetcode, so that's gone. This is going to be, let's just call this change. And then I want to actually just return change -1. So let's try it again with 8441. Let's try it with 7168. Yep. Is this faster? Who knows? Apparently it is. So this to me feels a little bit wasteful. We compute every intermediate value regardless of whether we need it, whereas before we only computed the values we definitely needed. I guess Python's function calls are very expensive, so that's probably what was taking us the extra time. It's a bit annoying that the timing has been set up so tightly and so fragilely. Like, I was passing them in isolation down here, but it was just when I was running them all together it got a little bit too slow. So that's a shame on the way this problem is set up. It basically forces you to do the one answer they're looking for rather than accepting viable alternatives. Yeah, it is what it is. I don't know. I'm disappointed in this problem, basically. It's railroaded you a little bit too hard. Particularly given this bound here. Like, this is basically Python's recursion bound. Python limits you to 998 recursive steps or something like that. So this here strongly hints that you should be able to do it with recursion in Python, and you can't, effectively, or there's some optimization that I haven't noticed. Anyway, we got through it in a slightly more difficult way than I expected. For a medium, that's a bit nasty, forcing you to have to do it a particular way and to recognize that Python's function calls are too expensive to solve this problem. I don't know. Do let me know how you got on. Did you manage to do it with the recursive call? I'd very much like to know that. So anyway, that's it from me. I have a train to catch, and oh god, I'm running very late. It's going to be very tight to catch the train. And I remember to like, comment, subscribe, all that good stuff, and I will see you next time.